Hey, hi everyone. So today in this video we'll be talking about another Leetcode question, which is subarray sums divisible by k. So we have an array 4, 0, 1, 2, uh, 0, 2, and let's say -1, and here also let's say 2. And then we are given a k, and then we have to count how many subarrays exist which are divisible by k. So if I take the example of this array, and firstly also let me just write down the indices, then we'll talk. So this is 0, this is 1, 2, 3, 4, 5, and 6. And okay, so now let's talk about this and how. So we have to count how many subarrays exist such that they are divisible by 3. So I can pick this one. So subarray is -2, 0, and 2, and its sum is 0. So 0 is divisible by 3. And what else? So I can also see this subarray if we expand on the both sides. So this is also one of the subarrays: 1, -2, 0, 2, and -1. This the subarray sum of this array is also 0. So I can see 2. There could be more. So 4 and 2 is 2. 2 plus 1 is 3. So 4, 0, 1, and -2. This is also one of the subarrays. And so 4, 0, 1, -2, 0. This is also one of the subarrays which has 0 sum, and then again 4, 0, 1, -2, 0, 2, and -1. So these two check out, these two check out. So no, it's not going to be divisible by 3, but if we remove this, then this subarray can be divisible by 3. So yeah, in this manner we have to return how many subarrays exist such that they are divisible by 3. So such that their sum is divisible by 3. So let's try to understand how actually numbers exist in real life. So if let's go into number theory just little bit, just basic number theory. So if if we have to represent any number in form of 3, so number theory states that any number in the world can be represented in this form: 3q plus r, where q is your quotient and r is your remainder. So let's try to pick any number. Let's say 31. So 31 can be written as 3 into 10 plus 1. And 32 can be written as 3 into 10 plus 2. 33, so 33 can be written as 3 into 10, oh sorry, 3 into 11. So yeah, and number theory states that any number can be represented as 3q plus 1, 3q plus r, where r is in range of 0 to 2, right? It's always going to be in this range. And yeah, so now let's try and just write some numbers. So like 0, 0, 1, 2, 3, and 4. So when we divide 0, remainder is 0, right? When we divide by then we divide 1 by 3, the remainder is 1. When we divide 2 by 3, the remainder is 2. Now here the remainder is 0, and now the remainder is 1. And if for 5 we try to write this, the remainder is 2. For 6, remainder is 0. So if we observe carefully, we see that these numbers or the reminders, they are repeating, and there is a there is a pattern here. The pattern is that the numbers of form 3q plus r repeat. So 3q will repeat after every 3 numbers. The number of form 3q will repeat. The numbers of 3q plus 1 will also repeat after every third, I mean every third number. If we try to produce these on the number line, every third number will be of this form. 3q plus 2 will also repeat. So for example, let's say 2, it's of form 3q plus 2. If we add 3 to it, we get to another number which is of form 3q plus 2, which is this number. Now if I have to uh, keep getting these numbers. So what will be the third number? The third number will be 8. Then another number will be 11. Now another number will be 14. All of these have gap of 3, and all of these have are of form 3 into q plus 2. So it's 3 multiplied, it's basically 12 plus 2. It's 9 plus 2, 11. 8 is 6 plus 2. And this also repeat for big numbers. So if we take the case of 379 or 378, I don't know which is that. I think 380 should be that. So 380 can be written as 378 plus 2, and 378 can be written as some 126, I think 126 multiplied by 3 plus 2, right? So this is something that we needed to understand. Now let's let's uh, uh, let's see how we can use this information in our subarray sum problem. So let's say we are given an array, and let's say subarray sum from starting till this position is, let's say, 7. And if we take this if we divide it by 7, we get remainder of 1. So what are we trying to do is that, so what are we trying to check is that if this subarray has to be divisible by 3. If it's divisible by 3, its remainder will obviously be 0. So if it is divisible by 3, then obviously if we have reached this position R, and at this position your remainder is 1, then definitely this position must have been reached by adding 3 to some previous subarray. So if there exists a subarray already which has the remainder of 1, so for example, if there is a subarray which has subarray sum of 4, and if we add 4 to it, then we would reach subarray sum of 7. So if we have an if we have a subarray which has remainder of 1 from 0 to rth index, what we are trying to do is, and we'll be maintaining these reminders in some sort of data structure. So, and if we have a reminder 1 earlier in our array, then that should mean that subarray sum of the remaining part, which is this part, is going to be 0. I mean, the remainder of this subarray sum is going to be 0, and hence this subarray will be divisible by 3, right? So that is the heart of our algorithm, and I'll try to I will try to show you in three or four more, one or two more examples. So let's say subarray sum from this position to this position is 5, and subarray sum from this position to this position is 5. If we try to take modulo of it from 3, remainder is 2. So what we are interested in finding is that whether there exists a subarray which has some, which is divisible, I mean which gives the remainder of 2 when we try to divide it by 3. What it would lead us to is, so if there exists a subarray which has a remainder of 2, then if there exists another subarray which gives us the remainder of 2, then this subarray should be divisible by 3, divisible by 3. And so what can be the eligible subarray sums at this position? It can be 2, right? So if we take 2, then the subarray sum from this position to this position is 5, this is 3, then this becomes then this subarray sum becomes 3, and it is divisible by 3. And it can be negative also. So for example, if subarray sum from this position to this position is 12, and subarray sum from, no, 12 is divisible by 3, right? We are interested in finding 3q plus 2 type of numbers. So 9 plus 2, 11. So if subarray sum of this, so if subarray sum from here till here is 5, and subarray sum of this subarray is 11, then that means the subarray sum of this remaining position is 6, and I mean the subarray sum from this position to this position is -6, and -6 is divisible by 3. So in this manner we are going to keep track of our subarrays, right? And yeah, So this is what is the idea behind this question. And so if we take example of 3, so we understand that any number can be represented as 3q plus r. R can be either 0, 1 or 2. But since we can also have negative values in our subarray, so for example, we can have this subarray also minus 1, minus 1, minus 1. Uh, what should I keep here? Okay, I'll keep here 0 and then minus 1. So if we keep track of subarray sum, so subarray sum at this position is 0, at this position it's minus 1, it's minus 2, it's minus 3, then uh, the at this position it's minus 3, and at here it's minus 4. So in this type of scenario, um, our code might lead to some extra cases, or maybe and we'll try to find what to do in these scenarios also. So maybe here, rather than minus 4, I can do something like let's say 8, and here the sum then becomes 5, and then I'll do a minus 2, right? So the sum will become 3. So if we observe carefully, the subarray sum from this position to this position is 3, and subarray sum from this position to this position is 0. So should give us this should be divisible by 3. So let's try minus 3. uh, so minus 3, 8, 5, 5 minus 2 is 3. So yeah, but mm, so from this position to this position it's 3, and what was I saying? I lost track of what I was saying. Yeah, we were basically talking about how to deal with negative integers. So yeah, let's take a look at this example. So if uh, if you have understood previous something from our previous analysis, what we're trying to do is we are maintaining a subarray sum, and then we are trying to keep track of reminders also. And also I think it's pretty clear from previous videos that if we are keeping track, if we want count, then just to avoid losing out some potential answers, we will be keeping track of frequency. So if it's not clear, I'll maybe give you another example, and then we'll try to understand why we are also interested in mapping frequencies. So let's say subarray sum from here till here it's 1, not 1, maybe 16. So 16 is 15 plus 1, so this is of 3q plus 1 form. And let me make it a bit bigger. So subarray sum from this position to this position is 16. Give me a minute. So let's say subarray sum from this position to this position is 16, and subarray sum from here till here is 1. So that should mean subarray sum from here till here is 2. So that should be part of our subarray. But subarray sum from here till here, I mean the remainder of uh, I mean, let's say, okay, we can take either, anything, it doesn't matter. So subarray sum from here till here is 10, and subarray sum from here till here is 7. So we see that here from here till here the sum should be 15, from here till here such the sum should be, yeah, 6, and from here till here the sum should be 9. All of them are divisible by 3, and since we are mostly interested in remainder, because remainder is going to tell us whether this sum is divisible by 3 or not. So let's say uh, so subarray sums are given. So if we take 1, it's already 1. If subarray sum is 10, then remainder is, the remainder is 1. And for this also the remainder is 1. So if we have 3 occurrences where remainder is 1, so we will have 3 more subarrays which are divisible by 3, right? So we are required to keep track of the frequency. So that is why we are going to be uh, keeping track of the frequency of how many times a reminder has come. And also at every instance when we are looping through this array. At every index we are maintaining a sum, then calculating remainder of it. And once we have calculated the remainder, we are going to check whether that remainder already exists or not. So for and not just a reminder, we are we need two things. Does a reminder uh, does the reminder exist or not, and if so, what is the frequency of it? So for this reason we will be maintaining a map to uh, store both these informations. So so let's say initially our subarray sum is 0, reminder is 0, and frequency is 1. Now we come here, subarray sum becomes 0, reminder becomes 0, and frequency becomes 2. But okay, I did something wrong. So when we are iterating, we see the subarray sum is 0 and the remainder is 0. So what are we going to check at every index whether that reminder exists earlier or not. So when we have not iterated, we are at this position and subarray sum is 0 and remainder is 0. And when we reach here, remainder is still 0, which means that this part should ideally be divisible by 3. So is 0 divisible by 3? Yes, 0 is divisible by 3. So uh, we keep track of this 1 and then we increase the frequency of 0 to 2. Now we move forward, our subarray sum becomes minus 1, and this was one of the edge cases that I wanted to talk about. So let's say when you divide minus 1 by, I mean when you divide minus 1 by 3, it will give you the remainder of minus 1. But what are we going to do in the negative cases? So the purpose is basically to see what are we going to do in negative cases. So for minus 1 can also be represented as 3 into minus 1 plus 2. This becomes minus 3 plus 2, because in number theory uh, we always keep a reminder as positive, so this becomes minus 1. So that can be one of the approaches. So that can be one of the approaches that we can take to solve this kind of problem. So if your reminder is negative, what have we done is, so any number can be represented as 3q plus r, but if your r is negative, what we can do is we can add and subtract minus 3 here, and then we can club this. So r plus 3, it is going to give us r dash, which will always be greater than 0, greater than equals to 0, and 3, I mean q dash, yeah, so 3q minus 1 becomes 3q dash 2. So it becomes 3q dash plus r dash, right? So that is one of the things that we can do. And so if we ever come across a negative scenario, what we can do is what we can do is we can transform this reminder to make it a positive, right? And so if we do that, we see that subarray sum is here minus 1, and minus 1 can be written as 3 into minus 1 plus 2. So this becomes your reminder. So this becomes your reminder. And then we see does 2 already exist in our hash map or not. If it does not exist, we simply update the frequency. If it had existed, so what it would have given us was, from here till here there exists a 2, and let's say from here till here and from here till here two subarray exists such that the subarray sum when divided by 3 gives you the remainder of 2. So if there were two subarrays uh, that that existed such that the remainder was 0, so we would have gained additional two subarrays for which the divisibility by 3 exists, right? Give me a minute, I'll just plug in my charger. Yeah, so if there where was I? Yeah, so it had existed, we would increase our count variable by the frequency of 2. So since that's not the case, we move forward, and here our subarray sum becomes -2. For -2 will add by 3, which will give us the remainder of 1. Here we see that whether 1 exists in our hash map or not, or yeah, whether this exists in our map or not. So since it does not, we'll again update the frequency of 1. Here it becomes -3, so -3 can be written as -3 into 1 plus 0, so it's 0. So now we see that 0 exists twice, right? So if I move forward, so from here till here, your remainder is 0. From here, your remainder is 0. Then this means that this subarray should also have remainder of 0, which it does. So we'll update the count variable. But there also exists a subarray such that the subarray sum this subarray sum is divisible by 3. So we see that there clearly exists such subarray. So we'll update our count variable to the frequency of 0, and then we will also update the frequency of 0 to 3. Now again here your subarray sum becomes 3, remainder again gives you 0, so we'll update this. Before updating, we'll update the count variable to the frequency of 0, which is 3, and then we'll update the frequency of 0 to 4. Now we do 8 minus 5, 8 minus 3, which is 5. Now if we take the remainder of it, this becomes 2. So we see whether 2 occurs, whether 2 exists or not. In fact, it does exist. So we'll update our count with the frequency, and then we update the frequency, and now we take 5 minus 2 is 3, remainder is 0. What is the frequency of 0, which is 4? So we'll update the count variable and update the frequency. So with frequency will be 5. Once we are done iterating this array, all the result, the answer is going to be stored in our count variable, and we are going to return this count variable. So let's try and code this solution up. We were maintaining an unordered map of integer m, and what was the pairing? It was a reminder versus frequency. Will keep track of running sum in this, and what else? Count. So initiate count with 0. Now we are going to iterate our array. So okay, so maybe we did not need it. So okay, and when I add a to this, it becomes sum plus equals to a, and then if we I try to find a reminder, so sum modulo k if your reminder is negative. So what we were doing for negative reminders, we were adding k value, and now we are going to check whether this reminder exists in your map or not. If it exists in your map, we are going to update our count variable by the frequency of reminder. As if it doesn't, we will not add it, and after we have done, we will update the frequency of the reminder, and once we are done iterating through this loop, we'll update the count variable. But we also need to add the initial reminder 0 with frequency 0 or 1. So now let's try and run the solution. So these example test cases are passing. Now let me try and submit this. Okay, so we see that the we see that this example has passed. If I try to analyze the time complexity, we are simply running a for loop. We are doing this operation, but this operation is constant time, so your time complexity is constant. And for space complexity, or the auxiliary space, we have taken this map, but when it comes to actually what are we actually storing in our map. So what we are actually storing in our map is the reminder versus frequency pairing. So in the worst cases, we can have all the unique reminders, and since k is pretty large, it's of order, I mean, in the worst case, it's of order 10 to the power 4. So if your k is very large, let's say k is your 99, let's say k is your 9999. So in that case, in the worst case, we can have 0 to 99998, when the value of reminders can be this. So yeah, that is our worst case. So our unordered map has the worst space complexity of O of k. So I hope this solution did make sense to you. And yeah, and another thing that I am interested in uh, is there I mean, does there exist another way such that we don't have to actually convert the -1 subarray sum. I mean, what did I say? So if you guys remember, what I said was, where was it? Okay, so what I said was -1 can be treated the same as -1 plus 3, which is 2. So that was what I was saying. Uh, so every number exists in this form, and the reason I said this was I wanted this solution to be true to its number theory counterpart. So in number theory, every number can be represented as 3q plus r, but the caveat is that your r is always going to be positive. But we have seen that if we do -1 modulo 3, it's going to give us -1, not 3 into -2, which is minus, I mean, sorry. So if we do this, so 3 into -1, -3 plus 2. So -1 and 2 are basically same. So we did this because we wanted to make our reminder in this form always positive, because yeah, but in the actual code, when you do this, your reminder comes as -1. When you do this -2 divided in modulo 3, your reminder is actually going to be this. So let's verify this, and then now we will try to think what can we do, here. So let's say -2 modulo 3 -1 modulo 3. Let's have a look at our std out. So see, -2 modulo 3 is -2, -2 modulo -1 modulo 3 is -1, and it's going to be in all the solutions, -2 and -1, uh, -2 and -1. So I am also interested uh, in trying to find another approach. So like, do we really need to convert our negative reminders to positive? So I want a discussion on that, and this is going to be the, I mean, this is the way we are moving forward in this video. So let's try and see what's the scenario for us. So what can we take our subarray as? 0, 1, uh, maybe fill it from the left side. So no, 0, 1, 2, so the sum will be 3, and then here reminder will be 0, 1, 2, and then I'll do a -6. So your subarray sum, so subarray sum I'll write here. So our subarray sum will be -3, which is divisible by 0. Now I will do a -1, so our subarray sum will be -4, and it will either give a reminder of -1 or 2. So yeah, this is the case that I wanted. So okay, so this will give you -1, and this will give you what? -1, and then I'll again add -1, so 0. So it will keep here, I'll give a reminder of -1, and then I'll add -1, so it will give you -5, and the remainder will be -2. So this is what I'm trying to do, to check whether there exists a way to solve this problem. The reminder is negative also. So yeah, let's try and find out. Okay, so this is your array and your sum, reminder, and frequency. Alright, so initially sum is 0, reminder is 0, frequency is 1. Here sum is 0, reminder is 0, your frequency becomes 2, count gets plus equals to 1. So count gets 1. Now you come here, you see that 1 exists, and your reminder is 1, frequency becomes 1, nothing happens. Here your subarray sum becomes 3, you get a reminder of 0, so you add 2 more values, so it becomes 2, and you add plus 1 here, so your frequency of 0 becomes 3. Now if we add minus 6, it becomes minus 3, so your reminder again comes as 0 and it becomes 4, but you have to add 3, which was the earlier frequency. So now here comes the interesting part. So your subarray sum becomes minus 4, and when you do a modulo for this, it will give you minus 3. So we are not actually going to convert minus 1 to 2 by adding 3. We have taken the look at that solution. I'm just trying whether I can generate a way to do it, whether I can generate a way to do this without that. So a reminder becomes minus 1. So what do we need to understand is that minus 1 exists, right? If we take a look at number line, so from here till here reminder is 3, and from here till here, no, just the sum, right? So from here till here, the sum is 1. From here till here, your sum is 7, and that should give you the reminder of 6, and that is going to be divisible by 3. So now what are we going to do is we'll try to generate some numbers for this. So minus 1, what are going to be the numbers for number, it's going to be minus 1, it's also going to be minus 4, and it's also going to be what, minus 7. So from here till here, let's assume your sum is minus 1. Sorry, your sum is minus 1. So for, let's say this is the position that we want to look, but we don't know what is the reminder position that we should look in order to make this array divisible by 3. So let's try and make this divisible by 3 first, and then look what is the solution, what is the reminder of this sum that is coming up. So if I have to make this whole sub, not, we are not interested in making the whole sub array as divisible by, we should only take a look at this. So let's assume, let's take a normal number which is divisible by 3. Let's say 27. So 27 is going to be divisible by 3. It's going to give us reminder of 0. So if this has a reminder of 0, uh, so if this has a sum of 27, then it should have a sum of minus 28. So if we try to take a look at minus 28 can be written as minus 28, uh, minus 28 can be written as minus 27 minus 1. So yeah, that can be one of the solutions. So yeah, so for minus 1 also we are going to use the same technique of from here till here, from, why is it, okay, so from here till here our subarray sum has a reminder of minus 1. From here till here our subarray sum has a reminder of minus 1 also. So we can take a look at this, and this should be divisible by 3. But what about the positive integers? So let's say from here till here our reminder is minus 1. Let's say it's minus 1 is like minus 28 only, and from here till here your sum is minus 31. So minus 31, and this has a gap of 3. So yeah, this subarray will have uh, divisibility by 3. But what about positive integers? So if we take a look at it, we can see that if I write 25, So 25 minus 28, it has a difference of 28 plus 25, which is 43. 43 can be written as 42 plus 1. So is it going to be divisible by 3? It's not going to be divisible by 3 because it's going to be give us no. So 25 can be written as 24 plus 1. So for 3r plus 1, it's not going to give us the divisibility test. It's going to fail the divisibility test. Let's try some another number. So let's say 26. So 26 can be written as 24 plus 2. So if we take a look here and try to write 26, so 26 and minus 20 will minus 28 will have a difference of minus 28 minus 26. So this is going to be minus 54, and minus 54 is going to be divisible by 3. So this works. So we see that for negative integers, if it has a remainder of minus 1, then what we need to check is that whether there exists a subarray of minus 1, and also whether there exists, the same n. So this was our reminder, right? So reminder, and for 1 we also need to check whether it has the numbers of form 3k plus 2, right? So minus 1 corresponds to your 3k plus 2. So k plus rem, right? If it is negative, we are going to check this also. So if your reminder is negative, you need to add the counts of m of rem and also m of k plus rem. On the other hand, let's say your subarray sum has such that your reminder from here till here is 1. So let's say assume 16, and what are we interested in finding for 1? We are also interested in finding whether there exists a number of form 1, which let's say is 7. So for that it becomes 9. So yeah, it passes. Now we are also going to take a look at the numbers of form 3k plus 1, 3q minus 1 and 3q minus 2. So let's take the case of minus 7 first, and then we'll take the case of minus 8. So if your subarray sum is minus 7, so this becomes 23. So 23 minus 7 will make this subarray sum as 16, but 23 we see that it's not divisible by 3, so this the numbers of form 3q minus 1 are not eligible, right? Now let's see this case. So minus 8 equals to minus 3 into 2, or 3 into minus 2, and so minus 8 can be written as 3 into minus 2, which is minus 6 in this. So 3 cube minus 2 forms. So if we take an example of this, so 8 plus 16, 24. So subarray sum from this part to this part will be 24, right? So if your remainder is positive, then we need to check obviously for count of m of remainder, but you also need to take a look at numbers of form. So this is minus 2, right? So how do you express minus 2? 3. How do you express minus 2 from this? Uh, Reminder minus k. How do you express, how do you write minus 2? So 3q. What technique did I use for this? K plus rem. So 3 plus reminder was minus 1. So 3 plus reminder. Uh, did I do something wrong? So if reminder is negative, you could do k and you have to okay. And then if your reminder is positive, so for 1 you need to check for 1, but you also need to check for minus 2. So how do you get minus 2 from 1? 1 minus k. Okay. So rem minus k. Similarly for 2, you will check for 2 as well as you will check for minus 2. So I'll show you. So if your reminder is 2 and from here to here your reminder is 2, this becomes eligible. But This also becomes eligible if from here to here sum is -1, then this will become 3, right? So yeah, so that is what. So rem minus k. So now I am interested in writing the generalized case, and if we are able, if we can successfully achieve this, then we will not be needing to convert negative integers to positive integers. I mean the negative reminders to positive, right? So let's try. If RAM is negative, count मैं RAM को करूँ and RAM को करना है and क्या करना है k plus RAM को करूँ. If your RAM is greater than 0, then you add of RAM, m of RAM, and m of RAM minus k. So m of RAM and m of k plus RAM. I don't know. Can we do this? I don't know, man. We can simply write these two and let's try and see. So how it will go is sum plus equals to a of I, RAM equals to sum modulo k, and then you check if your RAM is greater than 0, greater than equals to 0. We'll be writing a code which is worse, but I am more interested in just checking does that code work or not. So yeah, we will actually do this. Mm. Okay, so what were we doing? An ordered map. Now I am going to delete this line, and what I'm going to do is if RAM is negative, then we need to search. If your RAM is negative, then I'm going to find this, and what else I was going to find. If m dot find for negative RAMs, what two values we want, m of RAM and m of k plus RAM. So m of k plus RAM, so k plus RAM exists, we also have to check that, and we are going to add that also, m of k plus RAM, and similarly for else if your reminder is greater than 0, greater than equals to, I will write greater than equals to. So if m dot find RAM is not equals to m dot end, I'll do count plus equals to m of RAM, and I'm also going to find m dot find k minus RAM. If it is positive, then what I'm going to do is RAM minus k, m dot end, and I'll be adding that to m of RAM minus k. RAM minus k tha na? RAM minus k, yeah. So okay, and now let's try and submit this solution. Is it going to work? I don't know, but RAM minus k, where is it? Okay, so these cases are passing. I don't know if our solution will work or not, but yeah, I expect some okay, so this is working. Perfect. Right? So we have seen first of all why did we actually convert this negative reminder to positive, but then we also saw the need of checking this. So yeah, I hope this last approach as well as the first approach made sense to you guys. And on that note, let's end this video. Thank you.